Yep. All right, here we go. We're going to talk about modeling with differential equations. Before we get to that, I want to go over a basic, we call this like a translation principle. If you were told that two quantities were proportional, then what would that mean to you? So, for example, if A is proportional to B, what does that mean to you? Well, it turns out that it should mean this, that you can write that A is equal to some constant times B, right? So if you know that A is proportional to B, then you can write this mathematical equation. And that should kind of make sense because you're basically just saying that A is some multiple of B. Maybe it's twice B, 3 times B, 4 times B, or K times B. So that's what it means when two quantities are proportional. All right. So this concept is huge in translating certain word problems. So let's just kind of drive this home before we move on. So what if you had blue square is proportional to red triangle? What would that mean? Well, that would mean that you can write blue square is going to equal some proportionality constant, which I use this K here, but you can really use anything. So I could say maybe C this time just to be different. C times red triangle. Okay, so if square is proportional to triangle, then square is some constant times that triangle. That is something you can write. Where really I can put anything in for square, anything in for triangle, and the green here, you can see how I color-coded it, is just a proportionality constant. All right, so now we're not necessarily going to see it this simple. You're going to see more verbiage like this. All right, what if dy dx, that's a derivative, right, is proportional to radical x? Well, here's the quantity dy dx, right? Here's the quantity radical x. If they are in fact proportional, then one would equal a multiple of the other. So dy dx would equal k times radical x. Okay, so that should hopefully make a little bit of sense here. Let's just finish it up, go straight translation. What if I was to tell you if the rate of change of volume with respect to time is proportional to the square of the volume? So that sounds a little bananas, but it really shouldn't, because how do you translate rate of change of volume and then this with respect to time? What does that sound like to you? It should sound like the derivative. So it's the derivative of volume, and then I said with respect to time. So it's dv dt. So that's the blue part there, right? And then you have equals, since we said is proportional, so then is some multiple times this second quantity, which is the square of the volume. Well, that's just volume squared. And this would be the differential equation that is modeling this relationship. Again, if the rate of change of volume with respect to time is proportional to the square of the volume, then I can write this differential equation. So over here, you kind of have like in words some real life phenomenon, and then we're modeling that with a differential equation. And that's kind of part of the goal of what we're doing today, albeit we're going to be specific to a certain type of model. All right, so speaking of exponential growth and decay, you've been doing this for quite some time now in your high school math lives. So what exactly is exponential growth? If I asked you for examples of exponential growth, you probably, after thinking about it for a little bit, again, you can pause the video here and think if you want for a second to give me some examples. When you come back now, all right, what are things in real life that kind of behave with exponential growth? Most people will say population, right? The more people that you have, the faster the population is going to grow, right? At least in the beginning, that is true, right? Because if you have more people making babies, and so on and so forth. Obviously, there's a limit to that, but for the initial part, we would say that population behaves like exponential growth. Eventually, you reach something called carrying capacity, but we're not going to get into that. That's logistics growth, which we're not going to worry about right now. All right, what else grows exponentially? Well, money does, right? If you have, you make a certain amount of interest when you put your money in the bank. The more money that you have present, the more money that you're going to make in interest, right? And so that is exponential growth. Bacteria, things like that. You can actually use the current situation going on right now, and you can see how things are growing exponentially, but I don't want to be too glum, whatever the word is. I'm not going to get into that. All right, so here we go. So this would be the word definition of exponential growth. Basically, a quantity is said to have exponential growth if at each instant in time its rate of increase is proportional to the amount present. So again, the more people you have present, the faster population is going to grow, right? The more money you have present in a bank account, the more money you're going to make in interest. So that's kind of what this is saying. Now, underlined growth and increase, because you could also have exponential decay with like radioactive isotopes, right? So if you wanted to change this to a decay paragraph, it would say a quantity is said to have exponential decay. Maybe we'll put that in parentheses. If at each instant in time its rate of, it wouldn't be increase now, it would be decrease is proportional to the quantity present. All right. So that is exponential growth. That is how it's defined. So it turns out that we can model this real life relationship with a differential equation. All right. So how are we going to do that? Well, maybe we'll pick a variable y to represent how much we have of something at a certain time t. So we're looking into finding out this function y of t, where y is amount at time t, right? So we're coming up with this function y. And maybe I'll draw like an arrow like that. All right, so let's translate this. So let's reread it. If at each instant's time its rate of increase, how do you represent rate of increase of some quantity, which by the way, now I'm calling y? Well, it would be the rate of increase with respect to time. So that would be represented as dy dt. Okay. Now we're saying is proportional, just like we did on that previous slide. So is my equal sign, proportional, some constant times the amount of quantity present. Well, y itself is representing the amount quantity present at a certain time t. So here is a differential equation modeling this real life phenomenon, specifically dy dt equals k times y. That is a differential equation for exponential growth. So this right here is your differential equation for exponential growth. So you're like, all right, that's pretty cool. Let's go ahead and solve that, right? Because we learned how to solve differential equations. So how do I solve differential equations in my Calc AB class? So the only technique you have to do, will be responsible for, is separation of variables. So like we've said in the past, the dy here is up top on the left side. That's going to dictate that the y's have to go to the left side. So let me divide both sides by y. All right, and that gets my y's over here. Then multiply both sides by dt. And now I have separated the variables. My y's are on my left side. My t's are on my right side. So once you have that, now you have the green light to integrate both sides, right? Now remember, your dy and your dt's have to be connected with multiplication. And if I wanted to, for note flavor, I can rewrite this as 1 over y dy equals k times dt, right? So they're both sides are in the Riemann integrable form. So I'll integrate the left side, I'll integrate the right side. Do you know a function whose derivative is 1 over y? You do. It's ln absolute value of y. All right. Do you know a function whose derivative is k? Now remember, k is a constant. So like if I said, do you know a function whose derivative is 5? You would say, probably would say 5x, right? But this is with respect to t. So you should say 5t, but it's not 5, it's k. So a function whose derivative is k would be kt. And if you left it here, as you've heard me say in the past, you would get hammered, because when you do an indefinite integral, you have to add that constant of integration. All right, I chose to add it to the right side. Technically, you add it to both sides. You subtract 1 over. It's still a constant. And then this is what you have. So if I wanted to solve for y now, which, by the way, y is representing the amount at any time t. So let me solve for that. What's the move here? The move is to exponentiate both sides. So e to the ln, they're going to cancel. Their inverse functions being composed. You're just going to get absolute value of y. And then remember, you have to e to the entire side over here. You can't e individually. So you end up getting that. So you're like, all right, so what was the story here? What was the little trick that we did? If you remember, we did kind of like a 7th grade property of exponents here, where we can separate this. So you can write this as e to the kt times e to the c, right? And that's because when you multiply two things with the same base, you add the exponents. I'm just using that in reverse. And at the end of the day, e to the c, that's just a number that could represent some constant. So I'm going to come over here now and I'm going to write, instead of e to the c times e to the kt, I'm going to pick a constant. I can't really use c. I can't use k because they're used up. Maybe I'll use capital I, e to the kt. And then, bablamo, notice what I just lost. I lost the absolute value bars. Why can I do that? Well, because if I'm doing constant times something, and I can basically dictate whether this constant is positive or negative based on initial values, then I don't really need to have the absolute value bars here, which would basically just say I have equal plus and minus of this expression. Okay, so now what is this? This would be my general solution for exponential growth or decay, depending on what k is, right? For exponential growth. And you're like, that's kind of interesting because that should look familiar to you. Maybe the letters don't look familiar, but recall you learned something back in the day. Maybe you remembered it as PERT, A equals PE to the RT, right? Where what were all these things, right? The A was the amount present at time t. Well, that's what my y is right here, amount present at time t. The p, I don't know if you remember, we call that the principal or the initial amount. Okay, E is Euler's number. R is the rate. Usually it was like the APR, right? It's the rate of increase, right? Or the rate of decrease. And then T is just time. And so that's your exponential model right there. And you're like, holy cow, I just derived basically PERT from this differential equation. So this is the differential equation for exponential growth, whereas this is the general solution or the model for y for exponential growth. But we can actually do better than this in that, right? This is the general solution. What if I wanted a particular solution? Well, I'd have to give you some type of initial value. So what if I did? What if I told you that at time 0, you had some initial value, which I'm going to symbolize y naught. You can really call it anything you want. I'm going to call it y naught. Let me plug this point now into here. So y naught would go in for y, and then 0 would go in for t, for time 0. And if you think about this, k times 0 is 0, e to the 0 is 1, you end up getting that y naught equals I, which is, that's kind of interesting. That's what we remember this as, right? P was the principal, the initial amount. Well, guess what? I, that value in front, is actually representative of the initial amount that you start with, initial amount of money you put in the bank, initial population, initial number of bacteria in a petri dish, whatever it actually is. So that's actually pretty cool that we started with some type of behavior that we observe in either real life or in banks, for example. We model it with a differential equation, and then we come up and solve that differential equation to get a model for the actual quantity. So like this equation here, PERT, right? That lets you forecast, what your population is going to be 10 years from now, or how much money you're going to have in the bank 20 years from now. And it all stemmed from modeling that kind of differential equation right there, which is actually pretty neat, okay? All right, so what are we going to do with this? We're going to kind of stick on this exponential growth, and here's the deal. Whenever they give you this specific differential equation or they specifically refer to exponential growth, this is the solution. So you don't need to go through and solve this thing every single time. You can jump from differential equation straight to the general solution depending on the context of the problem. All right, so let's actually get to do a problem here. But before I even say that, let me just kind of reiterate the concept here, right? We have the verbal description here, which I'll actually take the time to write out. When you know that the rate of increase, or it could be decrease, but I'll stick with increase for now, is proportional to amount present, whenever you see those words, then you know that the differential equation for that is going to be dy dt, or d, maybe I'll call it a this time so that we don't get hung up on the letter y, right? The rate of change of a with respect to time is proportional, there's that k, to the amount of a present. And you basically can change a to any variable you want, all right? Now, what else do we know? This is the differential equation, but you should also now know that the general solution, right? I don't have to go ahead and separate the variables and do that by hand anymore. I basically know that the general solution is going to be A, and it's really A of t. A is a function of time, some initial amount, E to the K times T. All right, so you can make that jump. So these three things are connected in your brain and they go hand in hand. All right. All right, so let's go ahead and do some problems now. So this video is definitely be a little bit longer than 15 minutes, but we got to do it. I won't give you a video for Tuesday. How about that? All right, so here we go. It says a puppy weighs 2 pounds at birth and 3.5 pounds 2 months later. All right, that's great to know. It says if the weight of the puppy during its first 6 months is increasing at a rate proportional to its weight. There is the key right there. The weight of the puppy, all right, during the first 6 months just means that this model is only valid for the first 6 months. All right, but here we go, is increasing at a rate proportional to its weight. So you have the rate of increase, all right, proportional to the amount of weight present, to the weight. So that right there lets you know, oh, I know I can write a differential equation modeling this relationship. All right, so how would I do that? Well, the rate of increase, that'd be dw dt. That's the rate of increase in the weight, right? Proportional to the amount of weight present. Okay, so that right there ends up being my differential equation for this relationship. Now, should I go through the process of separating the variables and solving this equation? I could, but it's a waste of time. You did it once. You don't have to do it again. For this and only this specific differential equation, I have to be very clear about that. For this specific differential equation, when you recognize it's the one for exponential growth, you know that the general solution is going to look something like this. W of t equals W naught, that's the initial weight, E to the whatever K is times T, okay? And this is the differential equation, this is the general solution. So now you're like, all right, do you know any of these things? All right, let's go back to this screen. And you do, right? You know what Y naught is, the initial weight. They told you a puppy weighs 2 pounds at birth. So birth is like time equals 0. Yes. So you know that W of 0 is 2. So that's going to make this 2. So this ends up being 2 right there. All right. So we're still not out of the woods, unfortunately. All right. So we end up getting that. We get this. And you're like, all right, so this is all good. So now let me ask or answer the question. Then how much will the puppy weigh when it's 3 months old? So that means I want to figure out the weight of the puppy when it's 3 months old. So the weight when the input is 3, okay? So you go to do this and it's like, all right, 2 times e to the, and all right, I know t is 3, but what you don't know, all right, is this. What is k? What is that rate or that proportionality constant, right? That rate of increase, right? Which in this case would be monthly, by the way, because everything's in months as opposed to years. How are you going to figure that out? Well, you're going to figure that out by using some other information. So it says, and here, 3.5 pounds 2 months later. So this is saying that W equals 3.5 when T equals 2. That's what you get from there. So now if I chuck that in, say right here, right, because this represents the amount you have after a certain time. So if I chuck 3.5 in for there equals 2 times e to the, I don't know what k is, but now in this instant, right, if I put 3.5 here, that means my time value here has to be 2, right? This is the amount present after this time. These go hand in hand. They're the point. So now you're like, oh, that's pretty neat because what does that allow you to solve for? It allows you to solve for k. First thing I might do is divide both sides by 2. If I do that, it works out pretty decently. I get 1.75 equals e to the 2k. How do you solve for k here? All right, and this is basically your pre-calc world coming into play here. You got to ln both sides. So you're going to ln this side, and you're going to ln this side. Now the ln of e to the 2k is just 2k. You're composing a function and its inverse. A lot of you mo's out there like to put the 2k in front using the property of logarithms. 2k times the ln of e. The ln of e is 1 because e raised to the 1 is e. You could do that too. All right. I'm just going to choose to make it nice and streamlined. Clean it up and then divide by k by multiplying both sides by half. And now K is going to equal this. Now, if this is a calc question, which it was, this is an actual question from a multiple choice question on an AP exam, all right, you would put this in your calculator, and then I would store the value as K. So I type this in my calculator. When you end up doing that, I forget what you get. I think it's like, actually, I didn't do it. All right. So whatever it is, you get some decimal value here. Okay. And when you end up doing that, I would store it as K. And so now what I can do is I can come back to answer this question now. So this here is K, but I just defined what K is. So literally, if I type this in my calculator now, right, I'm going to be able to get the exact value. And when you do that, you do end up getting, let's see here, 4.630 dot, dot, dot. So how much will the puppy weigh when it's 3 months old? About 4.6 pounds. All right. So it's kind of like a two-part question there. Some pre-calc stuff involved and some calculus stuff involved. So definitely not maybe a bad idea for you to replay me going through that if you didn't kind of follow that. All right. So let's just move on to the next one here. All right. So let's take a look. It says population Y grows according to the equation dy dt equals K times Y, where K is a constant and T is measured now in years. It says if the population doubles every 10 years, then what's the value of K? All right, so this is obviously pretty important information here. But if this is where you stop, if you just translate, actually not even translating, if you just stop with what they're given, then you're not going to get very far. So you have to recognize that this is the differential equation, right, for exponential growth. So then if you want, knock yourself out, go ahead, separate the variables and solve. But you should know by now that if you solve that, you're going to get basically PERT, right? Or in this case with the Y, it's going to be Y of T equals initial amount, Y naught I'm calling it, but you can call it whatever you want, E to the K times T. This is your general solution for exponential growth, right? They go hand in hand. If you're given this, you can say that. Likewise, if you were given this, you can say that. It's like a two-way street here, all right? They go together. So now how do I answer this question? What's the value of K? I'm trying to figure out what K is, right? I'm trying to figure out what this is if the population doubles every 10 years. All right, well, first off, what does it mean that the population doubles? Because, by the way, I don't even know the initial population in this problem. They didn't give it to me. I just know the initial population is the initial population. So I'm representing that as Y naught. So then what would double that be? Well, wouldn't it just be 2Y naught, right? So it doesn't matter what you start here. I think back in the day, your middle school teachers like, just put a number in, put 100 in, and then put 200 over here. There's really no need to do that, right? So whatever your initial amount is, double it is going to be that. Now, this is really not good form for me to write it this way, right? So here's the deal. If I'm going to go ahead and put 2 of the initial amount here, so twice the amount, then I need to put the correct time when that happens. And it says the population doubles every 10 years. So if I put 10 in for the time, then I have the green light to put twice the initial right here. So now this is a complete equation, which at first glance you're thinking, yeah, but you have 2 unknowns. How are you going to solve for K? Well, what happens with the Y naughts? All right. Obviously, you can divide both sides by Y naught. And if you divide both sides by Y naught, the Y naughts are gonzo. All right. So then what do you end up getting? You end up getting that 2 equals E to the 10K. How do I solve this for K? Just like before, you want to bring that variable down. The way to do that, ln both sides. So that you're going to get the ln of E to the 10K, right? If you want to go kitty style, bring the 10K down in front times ln of E. And remember that the ln of E equals 1 because the ln of E means log of E base E, right? So you'd be asking yourself, blue E raised to what gives me black E? That would be 1. Okay, so you could do it that way, or you could just know that ln and E, they're inverse functions. You're composing them together. They're going to cancel. You're going to go in a loop. You're going to get 10K here. All right, and then to solve for K, maybe divide both sides by 10. Ln of 2 divided by 10 maybe on one of your science reference sheets, you have something like this, ln of 2 divided by the half-life time, or maybe if it's the decimal version of this, like 0.69 something divided by 10, right? Long story short, this is what K is. And if you bang that out in your calculator, 0.069 dot, dot, dot is going to be what your growth constant is there, all right? And again, if you think about it, the only calculus here was for us to recognize that this meant that. And then it really became a pre-calc question in terms of figuring out that constant of integration. All right, not too bad. Let's rock and roll. Move on. This is a multiple choice question. All right, this isn't a whole bunch of parts here. So I'll write multiple choice so we don't get bananas. All right, so multiple choice. All right, a lot of people get this wrong, and they shouldn't. So it says if dy dt equals k times y, right? So you got that. And k is a non-zero constant, then y could be. So let me rewrite this over here. dy dt equals k times y. And then you got to figure out, well, then what could y be, right? Well, again, you see this specific differential equation, this specific one, amount of y, the rate of increase of y with respect to time, proportional to the amount of y present, that's exponential growth, which means the general solution is going to be fitting this form, that y or y of t, but maybe this time I'll just get lazy and call it y, is going to equal y naught, representative of initial amount, e to the kt. So this is what y looks like. So think about this. There's not a lot of work here. There's you knowing that this is exponential growth and you knowing that the solution to the exponential growth, that model for the population is bam, right there. So now you're going to pick the choice that kind of fits this mold, right? And there is only one choice. So this one you should get. So pause the video and pick it. Pause the video. I told you to pause it, Duff. Come on, we're waiting on you. All right, so we're back. So which one is it? It's got to be this guy, right? Y naught is the 2, e to the k times t. This looks nothing like that, all right? This kind of does, but there's this plus 3, but that's no good. Looks nothing like it and really looks nothing like it. So this was the answer, and this was literally taken straight from a released AP test, all right? Multiple choice question. All right, almost done. Hang in there. Let's rock and roll. Whoa, we're talking about hard-boiled eggs now. All right, now it's getting real. So here we go. Because a hard-boiled egg is removed from a pot of water and set on a table to cool. So make sure you draw that table with your egg there, steaming. All right, you actually don't have to draw that. It says the rate of change of the egg's temperature. Well, this is where it gets interesting. The rate of change of the egg's temperature T with respect to time. How do you translate that? Rate of change, we're thinking derivative. Temperature, we're thinking T. With respect to time, we're thinking dt, right? So it would be like dt, rate of change of temperature with respect to time, that's equals proportional. We started the lesson off with this, k times. And now what's this say? To the difference between the egg's temperature and the room temperature, which is 72 degrees Fahrenheit. So the egg's temperature and the room temperature. So we're assuming the egg's going to be hotter if we just boiled it and it's cooling down. So it's going to be greater than 72. So I'll lead with that. So the temperature of the egg would be T, and then minus the room temperature, 72 degrees, right? So there's proportional to the difference between the temperature of the egg and the room temperature. And that's the differential equation for that. All right, and if we wanted to solve this, it looks like we could actually do it pretty easily, right, by separating the variables and go get them. This question didn't ask for that. It just said write the differential equation that models this behavior. So this is the real life phenomenon that models what's going on here. If I wanted to come up with a model for the actual temperature of the egg at any time t, right, I would just separate the variables and solve it. Right, that's the beauty of differential equations. All right, almost there. Let's take a look at this guy. This, again, is a multiple choice. This isn't 4 parts. Don't try and do 4 questions here. Multiple choice. Taken straight from an AP exam. All right, so here we go. It says the rate of change of volume with respect to time. So again, as soon as you read that, rate of change of volume with respect to time, it should be automatic that you're thinking rate of change of volume, dV, with respect to time, dt, right? And you can see all of these have that in them. all right, of water leaking from a tank is proportional, right? So we got is proportional. So is equals proportional K times the cube of the volume. So the cube of the volume is volume cubed. So this is the differential equation that models that first sentence. So now the question was, which of the following differential equations could describe this relationship? That should be one word. I don't know why that's broken up like that. All right, so what's the story? So you look at this and you're like, I get this is the distractor. This is like cube of time, not cube of volume. So it's definitely not that. All right, so see you later. Again, cube of time, see you later. And then you're like, all right, so this fits it. dv/dt equals, it looks like here's a k, right? That's like your k times that. But then you're like, well, wait a minute. This guy also fits the mold as well because that's a constant times volume cubed, constant times volume cubed, right? So both of these fit this model right there. So the question is, well, which one is it? Because they're not both right, and it's multiple choice. So I'll give you 2 seconds here, pause the video, see if you can figure it out. All right, so you're back. So did you figure it out? What are we missing? Water is leaking from the tank. If water is leaking from the tank, then what is happening to the volume? The volume must be decreasing. Well, if the volume is decreasing, then your derivative of volume, your dv/dt, must be what? Must be negative. All right, so it's got to be this guy. It can't be that guy. Okay? Sound good? All right, so there we go. So that's it. So that's all I wanted to do with you. I know it's a little longer than expected. I will not put another video up on Tuesday. This will be Monday's video. Your homework is going to be done a little bit differently in that it's really just for me to see these notes. So in your folder, just post you writing these notes and writing extra stuff, not just what you see on the screen, but as if you're in college and you were taking notes so that you can go back and use this. So do that for me. Your homework assignment for this is going to be a college AP classroom. So it'll be assigned on Monday. It's a bunch of questions. I'm not going to give you just one day to do it. I'm going to assign it on Monday. I'm going to make it due on Friday. All right. So I'm giving you a lot of time. So do not wait till Friday to do it because it's not the type of thing you want to do in one sitting. All right. I would suggest that you start it, you do it, and you ask me questions if you get stumped. And what I will do if questions are asked is I will post a video of me answering the question. All right. It would be in your best interest to do that. And that's it, guys. No more new material. We are done. Feel good about yourself. You learned Calculus AB in its entirety. After this unit, we will start to review. All right. Hope everyone's safe. Be good. Peace out, Cub Scout.